Hello everyone, welcome to Computer Science and IT Gate Coaching. Don't forget to subscribe my channel and press the bell icon to get the instant notification of my free lecture. So this is about me. I am a computer science gate faculty having more than 5 plus of teaching experience, mentored more than 50,000 students, taught in different coaching institute all over India. Okay, it's like the Gate Academy, even qualified multiple times Gate, and even I have given the coaching in many government colleges as well as in many private colleges. Like in SRM Chennai, I have given coaching. CAT Bhubaneswar, I have given. BC Bhagalpur, Jorhat College of Engineering, Guwahati University, Dibrugarh University, Government College of Engineering and Technology, Jammu, Ramgarh Engineering College. Okay, these are the colleges where I have went and I have given the coaching. So now in this lecture, we are going to start heap part. So we have seen the introduction. We have seen of data structure, tree data structure. Then we have seen some why we should study heap. Okay, now we will see for complete binary tree also we have seen. Now we will start Max-Heapify. Okay, so the things that is required for heap sort, now we are going to start. So first you need to know starting leaf node. So right, starting index starting index of leaf node, starting index of leaf nodes, or complete starting index of leaf node of a complete binary tree. So of a complete binary tree, what is the going to the starting index? Okay, index is starting from 1. Okay, so starting index of leaf node of a complete binary tree, complete complete binary tree, a complete binary tree. So what is the starting index of a leaf node of a complete binary tree? Okay, you are having a binary tree, complete binary tree. We are asking you what is the starting index of the leaf node of a complete binary tree. So let me take an example. Like if you are having a node, if you are having a tree like 0, then 1, then here, then again here, then here, then here, then here. Now see, this is the, so index is going to 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the index, not the value. 10, 11, 12, 13, 14, and 15 till 15. Okay, now what is going to be the starting index? So starting index is going to be the floor of n by 2 plus 1 plus 1 to n. Floor of n by 2 plus 1, let me write, floor of n by 2, floor of n by 2, n is the number of nodes. Okay, floor of n by 2 plus 1 to n. N is number of nodes. Okay, n is number of nodes. So your total number of nodes is, you are having 15. So 15 by 2 of floor is going to your, what is 15 by 2 is your 7.5. So floor of 7.5, floor of 7.5 is going to your, 7 to 15 is going to your 7. 7 plus 1 is 8. 8 to 15. So starting index see 8, 9, 10, 11, 12, 13, 14, 15. So it's 12, it's 13, it's 14, it's 15. So a starting index of a leaf node of a complete binary tree is going to start from floor of n by 2 plus 1 to n. Okay, floor of n by 2 plus 1 to n. So you write the starting index, the starting index, the starting index of leaf node, the starting index of leaf nodes of a complete binary tree, a complete binary tree, a complete binary tree having having n nodes is floor of n by 2 plus 1 to n. Floor of n by 2 plus 1. Okay, this is the starting index of a complete binary tree having n nodes. Now we are going to see maximum number of nodes at a given level of height h. Okay, so I am asking maximum number of nodes at a given level of height h. Maximum number of nodes at a given level of height h of a complete binary tree. Okay, so let me take that. So if you have not written, then you take the screenshot. Okay, now see maximum number of nodes, maximum number of maximum number of nodes, maximum number of nodes at a given height, at a given level, at a given level of height h, at a given level of height h, of height h, of complete binary tree, complete binary, complete binary. I'm saying complete binary tree. What is going to the maximum number of nodes? I'm asking about maximum number of a nodes at a given level of height h. If height is 1, if that position height is 1, height is 2, then what is going to be the maximum number of nodes? Okay, so let me take an example. Now see, this I am going to take, and this is your complete binary tree. So in complete binary tree, you know that it will first have left child, then only it can have the right child. Okay, so it is saying that, so maximum number of nodes at a given level of height. Now this is having height 0. How many maximum nodes is having at height 0? 1, 2, 3, 4, 5, 6, 7, 8. 8. Height is 1. How many nodes are there having height 1? 1, 2, 3, 4. How many nodes we are having of height 2? 2. And height 3. How many nodes? 1. So maximum nodes, okay, that is going to be your, see, maximum number of nodes at a given level of height h of a complete binary tree is 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 seal of n by 2 to the power h plus 1. Seal of n by 2 to, this two formula is very important. This two formula is very important. N by 2 to the power h plus 1, where n is total number of nodes, where n is total number of, where n is total number of nodes, where n is total number of nodes in a tree, where n is total number of nodes in a tree. Okay, where n, so your formula is n floor ceiling of n by 2 to the power h plus 1. N is total. So here total number of nodes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1 minute. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 nodes is there. So n is here 15. Now I'm asking you, how maximum number of nodes at height 0. Maximum number of nodes. Maximum number of nodes at height 0. At height 0. Now I'm asking maximum number of nodes at height 0. So that is going to be a floor of n by 2 to the power h plus 1 by 2. Okay, floor of n by 2 to the power h plus 1. N is your 15. Height, you are saying height 0. So that is going to be 0 plus 1 is only 2. Now, the floor of that is going to your 7.5. Now you are asking the seal of that. Sorry, seal. So seal is going to take the upper number, that is 8. So see, maximum number of nodes you are getting 1, 2, 3, 4, 5, 6, 7, 8. So maximum number of nodes at a given level of height 0 is going to this. Okay, it is going to be a seal of, is going to be 8. So now maximum number of nodes, it is saying maximum. Okay, maximum number of nodes, maximum number of nodes, maximum number of nodes of height 1, of height 1 I am saying. So is going to be seal of n by 2 to the power h plus 1 seal. So a number of nodes here is 15, and here 2 to the power height is your 1, 1 plus 1, 2. So that is seal of 15 by 2 to the power 2 is your 4. So that is going to be 3 point something. 3 point something we are going to get. So flow ceiling is going to your 4. Seal is going to your 4. Understood. And you have seen that the maximum number of nodes you can get in a complete binary tree of height 1 is 4. Height 2, 2. Height 3, 1. Am I clear to all of you? Anyone having any doubt, please let me know. Fine. Hope it is clear to all of you. Now we are going to see one function that is called as Max-Heapify. Now what is Max-Heapify? See, we are going to build max-heap or other mean heap. So here we are going to max. So max-heap is a your is a function. Okay, is a function which is going to make which is going to make max-heap. Okay, how? So if I will give you one left subtree which is already a maximum, which is already a max like 14, 8, 7, then 2, 4, here 6. So it is having a max, you see, 14 maximum from all its children, 8 maximum, 7 is maximum 2. So So the parent should be maximum for all its descendant. So it is maximum 14. Now I am taking one right subtree that is having 10, then 9, then 3. It is a max. See, this is also having a max. So your left subtree is having a max. This right subtree is having. Now I will add one root. I will add one node at the root. What I will do, I will take two max and one I will consider as a left subtree, and another I will have the right subtree. Another I will have the right subtree. Now my work is that now right subtree. Now I will add one node. I will add one node at the root. So let us assume with 1. Now it is not a maximum. See, maximum is not there. So max heapify is a function. So if your left subtree is your max heap and if your right subtree is your max heap, then if you'll add any node at the root, then max heap, if you'll call max heapify on this tree, max heapify will return a max heap. It will make a max heap. How it will make a max heap to this tree? It will check whether the left child of that, so write the index 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You know that if the index is 1, if it is starting from 1, left child index is going to 2i and right child index is going to 2i plus 1, means 2i plus 1. You will check whether the element that is present on left child, whether it is greater than its parent. Yes, it is greater. Then you will use one temporary variable that is largest. Okay, that will have the index of the largest element. Index, I'm not saying the it will have the element. You will find the largest. Index means the element. See, like in 1 and 14, which is the largest? 14 is largest, left child is largest. So index, so which index value is the largest? 2. Now you compare from parent and left child. Now we'll compare from the largest and from the right child. So largest index is 2, value is 14. Now 40, between 14 and 10, which is maximum? 14 is the maximum. So largest is going to have the index 2. See, largest is going to a temporary variable which is going to store the index, which is going to store the index of a element which is having the largest value. So now you find that out of these three, which is the largest? 14 is the largest. So with largest, you will swap the element that is present, that is the parent. With parent, you are going to swap with the largest index element. So these two will get swapped. So one will be here and 14 will be here. One will be here and 14 will be here. See, I'm after adding one root at the one root. Okay, means I have taken two left subtree and one right. I have taken one left subtree and one right subtree, and I have created one tree by adding a root. Now I want to make that tree to a max heap. So I am calling the max heap on the root. So after that we found, after one iteration we found that left child is having the maximum value. So that's why I swapped with left child with the root. Now, now, now see, now it is not. Now we hadn't got max heap because 14 is maximum, but one is not the maximum. See, one is not now. I will call Max-Heapify on one. So I will compare with its left child, which is greater. So what I am doing here, I am comparing with out of these three nodes, left child, right child, and the parent, which is having the maximum value. So 8 is having the maximum. So I will swap 8 here. So now largest is going to have the index 4. Largest is going to have the index 4. Is index 4, and I will swap here. 8 will be here and 1 will be here. 8 will be here and 1 will be here and 1 will be here and 1 will be here. Now again it is not max heap, so this swapping, after swapping I will call max heap here. So now largest will be 9. Largest index is going to be 9 because 4 is the maximum. Now 4 is the maximum. So largest index is now going to be 9, and then I will do this swap. So 4 will be here, 4 will become here and 1 will be there. So 4 here. Is it clear to all of you? So this we have done. Now see, you know that leaf is always going to your maximum because leaf is not having any child, neither left child nor right child. So it is going to maximum only. Am I clear? So after adding root to the left subtree and right subtree, you have to make a max heap tool. You have to make a max heap tool. So that's why we are having a function that will do like this: Max-Heapify. Okay, Max-Heapify is going to create a max heap if it's left child and right child. If it's left subtree is max heap and right subtree is a max heap. Now we will see the code. Anyone, if you're having any doubt, you can comment. Now see Max-Heapify. Max-Heapify. Now how we will write the code? So we are calling the Max-Heapify, the function, on the array A and the index I. The index is I and the array is A. You know that the formula to find the index of the left child is your 2 into I, 2 into I, and right child index is going to your. So let me first give one thing. When we can call left Max-Heapify, when we call Max-Heapify. So before writing the code, I should write that. So right, it is applied only if the it is applied it is very important. Okay, so you can't apply Max-Heapify on all the complete binary tree. You can apply only if only if the only if the left subtree only if the left subtree and the right subtree and the right subtree is Max-Heap. If the left subtree and the right subtree is Max-Heap, then only you can apply. This is a comment, multiple line comment I have closed here. Now, left child index is 2 into I, right child index is 2 into I plus 1. Okay. And you are using one largest temporary. This is the pseudocode I am writing. Okay. The left is 2 into I, right is 2 into I plus 1. So don't check here syntax error. Okay. Since it is pseudocode, in gate exam they will even give you pseudocode. Okay. This is pseudocode only. You have to just see the logic here. Now if left child index, if it is smaller than or equal to a dot heap size, see what can happen. Like, this is a code. Here we are smart, we are human, we are finding that when the index is 10, left side index is going to your 20, but we are not having any index which is having, which means we are not having any element which is having the index 20. So we need to check where it's the left child index should be smaller than, means inside that. So see here, heap size is here. How much is the heap size? Here heap size is your, see, all these things I have taught you. Heap size is going to your 10 here, is going to 10 here. Here it was having, here see, let me write. Initially, the tree was having here 14, here 8, here 4, and here it was having 1. Okay, here it was having 1. So it is a left subtree and it is a right subtree. It is a left subtree and it is a right subtree. So your left subtree is a max-heap and your right subtree is a max-heap. If this is true, then you can call the Max-Heapify on the root. Then you can call Max-Heapify on the root. Okay. And Max-Heapify, what it will do? Max-Heapify will make this tree as a max-heap. Then will make it as a max-heap. Now see here, it is 1. Now it is not maximum. Now it is not. See, now it is not maximum. But late subtree is a maximum because root is the maximum. But 1 is not maximum. So what we will do? We will check with the root, with the left child and with the right child, which is maximum. One will between 1, 14 and 10, which is maximum. 14 is maximum. So I will swap 14 here and I will write 1 here. I am swapping these two values. Now I will call Max-Heapify here. Why Max-Heapify here? Because 1 is not maximum here. See, because now your left child is not maximum because you have swapped here 1 and 14. So you have to call Max-Heapify here. Okay. So when you are calling Max-Heapify here, largest is here and here is 1. So I will swap. So between left child, right child and parent, 8 is the maximum. So I swap with that. Okay. Now, I will call Max-Heapify here. Now here between parent, left child and right child, which is maximum? Right child is maximum. So I will swap with the right child. And I will make here 1. Will make here 1. So 1 here, 4 here. Now see this. Now see, now the tree is maxi. Now the tree is maxi. Fine. See here. So when we are here, we are calling the Max-Heapify the function on the element A, means the array A and index I. So left child index is going to 2 into I, right child is this. Now we will need to check it whether left child index is within your array or not. So that should be smaller. Left child index should be smaller than a dot heap size, and we will check whether the element that is present on left, whether it is greater than the parent, whether it is greater than the, see, a dot is I parent, whether it is greater than the left child. If this is the case, then largest index is going to have L. Largest is going to have the left child index. Is it clear? See, I am checking. I find first left child index. Then with left child parent, with left child value and with the parent, I am comparing. If left child is having the largest value than the parent, then largest index is going to have L. Okay. Now, if this condition is false, then else, then which is going to be the largest? Means parent is going to be there. Then largest is going to having I. So largest is going to have the index of the element between left child and the parent, which is the maximum. If left child is maximum, the largest is going to have the index I. If parent is maximum, then it is going to have the index of the root. Else part is having largest equal to I. Now by comparing left child and right child, now between comparing left child and the parent, we got the largest index. Now with the largest we need to compare with the right child. Now with the largest we will compare. So now with largest index we need to compare. If right is smaller than a dot heap size, and we will check array R whether is it greater than a largest. Now the right child value I am comparing with the largest element. If if a dot right is greater, then largest is going to your R. Else part we know it is not required to write, because else part will have the largest as I. Okay, else part will have whether if it was having L or I, anything it will have. See, here with this code I am checking first between parent and left child which is the largest index, which element is having the largest value, and I am storing the index of that index. I am not storing the value, I am storing the index. So I find out that between left child and the parent which is having the largest element, we need to write largest equal to I, because here after comparing the parent and with the left child, I am getting which is the maximum, whether parent value is maximum or left child is greater. See, first these two code, after running these two code, we are getting largest equal to either this index or this index, now with this largest I am checking with the right child, if right child is greater, then largest is going to this, otherwise whatever it was between these two. That's why else part here it is not required. Okay, is it clear to all of you? So now we will check. Clear है ना सभी को? Is it clear to all of you? Anyone still having any doubt, then please comment. So first, between largest index is going to, we are finding between parent and the left child, we find the largest index. Then with the largest index we are checking whether the largest index that we have found, is it actually the largest or the right child is going to be the largest. If the right child is the largest, then largest is going to the index of the right child, else it will have the same whatever it was. So that's why here I am not writing the else part. Now after this we will check if 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 the largest index is not equal to the parent's index, means let us assume there can be some tree like here in ASL. If here I will add, now let's assume this is your left subtree and this is your right subtree. Now if the parent, if I am going to add 20, I am adding 20 at the root. Okay, now see, it is already a max heap. Left subtree is a max heap, right subtree is a max heap, and maximum element is at root. So when you are calling this max-heapify here, between these two, largest is your one. Now between largest and the right child, largest is again going to 1. So why to swap with its children? If largest is the parent index, if largest index is parent only, then it is actually a max heap. No need to call max-heapify again. See, here we were after swapping, here again we are calling the max-heapify. But if largest you are getting the parent only, means it is already a max heap. Okay. So we'll check if largest is not equal to parent index, means largest, the root element is the smallest. That's why we are going to either left child or right child. Okay, am I clear? So if I am going to either left and right, then we will call max-heapify on the largest index. So we will do swap on. So if this is the condition, if largest is not your parent, then swap with a of I and the largest, whichever is the largest. because with the parent you are going to swap. If the parent is only the largest value, if having the largest, then why to swap? So we will check if parent is not the largest, then swap, then again call the Max-Heapify, because after swapping it may happen that left subtree is not your Max-Heapify, because if I'll write here 1, then 1 will get swapped here with 10. So here it will come 1. Now this right subtree is not a, Max-Heap. Okay, if I'll add here 1, if I'll add here 1 or 2 here, let's assume, then between these three, which is maximum? This is maximum, so I need to swap. So largest with largest and with the parent I need to swap. So 10 will be here too. Now I need to call Max-Heapify here again, because now right subtree, because you have to do this swapping. It may happen. So after swapping, the condition may get violated. So you have to call Max-Heapify in the largest, because largest is 3. So first the largest was, now in between these two and 3, largest you found out that. So let me take with one by one, step by step I am showing. So here initially it was having 10. Here initially it was having 10. Okay, here initially it was having 10. And here it was having 10. I am adding here 2. So first I will compare between the parent and the left child. So between these two, which is the maximum? This is the maximum. So now largest is 2. Now with largest, and I will compare with the right child, right child. So largest is having the element 8 and right child is having the element 10. So this is maximum. So largest index is now going to 3. Now largest is not equal to index of the parent. No, it is not equal. So now you need to do the swapping between largest and the parent index. So this, and with this you are going to do swapping. So here it will be 2 and here it will be 10. So here it will be 2 and here it will be 10. Now again, now see, this is not, after swapping the condition may get violated. Now you have to call Max-Heapify here on array and on the largest index. So now index that where you are going to call is your Max-Heapify A on the largest, okay. Am I clear? Now you close the function. Now if largest is going to index I, no need to do anything. Means the tree is the maximum. Am I clear to all of you? Now see, with the I will execute the code. Now I will execute the code in a tree. First let me know whether it is clear or not. Anyone is still having any doubt? Now I will execute the code in a tree. I will take one tree where left child and right child is going to your left subtree and right subtree is going to your Rator is saying clear, sir. So one is there, here 14 is there, here 10 is there, then here 8, 7, 9, 3, 2, 4. Okay. Now see, we will execute the code. So this is the parent index I. Now I will calling the Max-Heapify on this array. See, I have taught you that you will store the complete binary tree in an array. So A is your array. The starting index is going to be 1, then 2, then 3, then 4, then 5, then 6, then 7, then 8, then 9, then 10. Okay, this is the case. Now see here, I you called, it is applied only if the left subtree and right subtree is a maxi. Yes, left subtree and right subtree is a maxi. Now you called the maximum. Left L is going to 2 into I. L is going to your 2 into I, 2, and right is going to your plus 1, that is 3. Now you are doing comparing whether L is smaller than A dot heap size. Heap size is your here 10. Heap size is your 10. Yes, it is smaller. It is smaller. Now you will check. I will check left is smaller than A dot heap size, and element that is present on left, is it greater than the element that is present on root root? So yes, it is greater. Left is greater. So largest is going to your L, that is 14. Largest is going to have L, that is 14. So else part will not get, so if part satisfied. After that, now we will go here. Now with right child and with the largest I'm going. So right index, is it smaller than A dot heap size? Yes. And AR is greater than A largest. AR is your 10. Is it greater than A largest? No, 14 is the greatest. So this here I will not go inside that. So largest will be as it is. So largest is will going to as it is 40. Not saying largest is not equal to I. Yeah, I is your 1 and largest is your 14. It's not equal. Now it's saying swap a element at I and element at largest. So these two will get swapped. Here 14 will come and here 1 will come and here 1 will come. Now, now after that it is calling max-heapify and a and largest. So now it will call max-heapify here. So now after that max-heapify is going to call on a and largest. So largest is your 14. So now a is going to your A is going to your array and now I is going to your 14. I is going to your 14. So see here. So that condition we are not checking here. See max if is saying that maximum element. It should have the maximum element. Okay. It should have the maximum element. Here duplicate value we are not allowing. Okay. I'm not allowing any duplicate value. So in the code we will mention that duplicate values are not allowed. So largest is index है ना? हाँ, largest is the index. Largest is going to have the index of the largest element. L is the index. Now you are going to see now I is your 14. Left child index is going to your 14 into sorry I is your no sorry I is your 2. I is your 2. I think I did somewhere one mistake. I should be your 2. Okay, मेरे से गलती हुआ है. Largest should be 2. Largest index should be 2. I think while writing I have did one mistake. Yeah, largest should be 2. Largest should be 2. It's a index. It's a index. Okay. So now it will call here 2. So I should be 2. I should be 2. Okay. Now left is going to 2 into 2 4 and right is going to have 5. Now I will check. Now I will check. L is smaller than A dot heap size. L is your 4. Yes, is smaller than A dot heap size. A dot A dot A4, that is the A4 is the largest. A4 left, is it greater than the element parent AI? A4 is it greater than this? Yes. Then largest is going to your 4. Largest is going to have 4. Now with the largest I will compare with the index at right. So now if part is R is smaller than A dot, yes, R is smaller than. So R is your 5. 5 is smaller than A dot heap size. A dot heap size is 10. And A right index element, is it greater than A largest element? So A largest is your 8 and A right is your 7. No, it is not greater. So largest will be as it is. Largest. So I will not go inside this body. Will not go inside this body. So now I will check if largest not equal to I. Largest not equal to I. Largest is your 4 and I is your 2. Yes, not equal to I. Then we will swap A largest and AI. So I will swap A largest and AI. So 8 will be here and 1 will be here. Now I will call again Max-Heapify on A and with the largest. So largest index is 4. So now I will be 4. See, the condition will get violated. That's why every time after swapping we are checking that whether if wherever I have swapped, whether in left child or right child, I will check whether after that it is satisfying the max heap or not. We can call the max heap here because left subtree and right subtree is max heap only. Okay. So now here I is your 4. Now left is going to your 8 and right is going to your 9. Now I will compare first with left child and with the parent, which is maximum. 2 is maximum. See, first L is smaller than A dot heap size. Yes, and A left element is greater than A dot AI. Yes, left element is greater than parent. So largest is going to your. So now largest is going to your 8. Now we will check this. If R is smaller than A dot A heap size, yes, because A heap size is your, see, A heap size is your 10. So 9 is smaller than that. And now we will check whether the A right is greater than the largest index element. So A8 is your 2 and A right is your 4. Now right child is the largest element. Right child. See here. So now AR is greater than A largest. So largest is going to R. So largest is going to R. So R is your 9. Or largest is going to 9. Now I will check if largest is not equal to I. Yes, largest is not equal to I. Now I will swap AI and A largest. So now I'm going to swap AI and A largest. Largest is this. So 4 will be here and 1 will be here and 1 will be here. Then again I will call Max-Heapify here. Then again I will call Max-Heapify on A and with largest is 9. Now its left child is your 18 and right child is your 19. See, max Heapify on A and 9, left child is your 18, then right child. Now see, if left child 18, is it smaller? No, heap size is your 10, it is not. Condition false. So now else is going to your largest is going to your I, means parent is the largest. Now parent is the largest. So largest is going to your 9, index 9. Okay. Now we will check right is smaller than no right subtree, so it's not smaller. Now largest is not equal to no, largest is I, means the element that where you have inserted, that is the largest only. No need to do any swapping. Now you got a max heap. Now you got a max heap. So this is the max heap only. No need to do any swapping. Now this will return here. Now this will return here. Now this will return anything. Now it is not doing anything else. So you got, after calling the max heap, you got a max heap. So you can call max-heapify only when the left subtree and the right subtree is a max heap. Now we will see time complexity and space complexity of max-heapify. Now you know that height of a complete binary tree at max is going to be log n. In verse type, so just to move one level down, you have to do two comparison and one swapping. One comparison, then another comparison. So just to move one level down, you are doing two comparison and one move. So at maximum, how many levels you will have? Log n. You will have log n. Okay, see right first. Time complexity. So just to move, just to move one level down, just to move one level down, we need we need two comparisons. We need, so just to move one level down, we need two comparisons. We need two comparison. We are comparing with left child and then right child. We need two comparisons and one swapping. We need two comparison and one swapping. We are doing one swapping. Okay, we are doing two comparison and doing one swapping. See, just to move one level down here, or just to go one level, we are doing one comparison, then one comparison, two comparison, and one swapping. One swapping. Okay, and one swapping. Therefore, 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 total number of comparison is required. Therefore, total number of comparison is required, because you know that height of the tree is going to log n. So therefore, total number of comparison is required. Is required. Therefore, total number of comparison is required is 2 into log n, 2 into log n, and log n swapping, and log n swapping, because that whatever is going to be the height, that many swapping we are doing, and log n swapping, and log n swapping, log n swapping for worst case. In worst case, you have to do that many number of comparison, whatever is 2 into that many, 2 into log n, and log n swapping, and log n swapping. Okay, and and for worst case. So total time complexity is going to, so total, please let first you write this, first you write this. If you're done with the writing, then you can comment. Okay, so just to move one level down, we need two comparison. We are doing two comparison and one swapping. So you know that height of the tree is going to be log n. Total number of comparison is required is 2 into log n, and log n swapping, and log n swapping for worst case. So total time complexity, the total time complexity, the total time complexity for worst case, and for even for your average case, is going to be same. And even for your average case, worst case, worst case, even for average case, it is going to your big O of log n. It is going to your 2 into log n plus log n. 2 into log n plus log n is going to your log n only. 2 into log n plus log n is going to log n. Okay. Now, what is going to be the best case time complexity? You people, please comment, and please comment. N is number of nodes. What is going to be the best case? You think little bit. What is going to be the best case? Average is always means almost going to be log n only. That way. In average, we need to go till uh, log n, means what can happen till log n by 2 height. When can be the average? When you are going to half of the tree. So that is going to your, that is going to take that many na, 2 into log of n, then log of n by 2. So if you are traveling half of the tree, then again in asymptotic wise it is going to be log of n. Are you getting that? In average case, you will go to half of the tree. In half, you got that. So the height of the tree is going to be we go of log n by 2 height of the tree. So that many compression you will do and that many swapping. So overall, it is going to take log n only. So best case is going to have the time complexity as big O of 1, and we can say as a omega, and we can say as a omega. So this I will say as a omega. Okay. When best case will happen, like this is the case, if you are having a tree, like you are having 8, 4, 7, 2, 1 and 6, and here you are having 10, and here you are having 9, and here you are 3. Now you are adding a tree node which is having 40. Now it is maximum only between left child and right child. This is max subtree, left subtree is maximum, right subtree is maximum. Left subtree is a maximum, right subtree is a maximum. Now you add a root here. Now this root element is maximum from this left child and right child. So you are only doing going to do two comparison and one and no swapping. Only two comparison you are doing. No swapping you are doing because largest is going to your I only. So you are not going to do swapping now. You are not going to again call the Max-Heapify on largest. See, this condition will be false. Largest is going to your one. So I, so largest is not equal, no, false. So nothing will happen. Only two comparison. So it's going to take constant time. That is going to omega. Is it clear to all of you? Time complexity. Anyone still having doubt? Then you can comment. Now we will see the space complexity. If anyone having doubt, you can comment. Otherwise, we will now go to space complexity. You know that in recursion, I have taught you in recursion how to find the space complexity. Space complexity. Since it is a recursive function, the space complexity will be the the height of the stack. Whatever will be the maximum height of the stack, that is going to be the space complexity. And maximum height in case of tree is going to be the what is the height of the tree. Whatever will be the height of the tree, that is going to be the maximum height. First you are calling Max-Heapify here, then here, then here, then here. Like Max-Heapify. First you called Max-Heapify on Max-Heapify here. Max-Heapify on Max-Heapify on A on 1. Then you call Max-Heapify on A on 2. Then you call Max-Heapify on A on, there you called 2. Then you called on 4. Then you called on 4 on 4. Then you called Max-Heapify on A, and after 4 you call Max-Heapify on 9 on 9 on 9 you call. So this will return. So this will return here. Then this will return here. Then this will return here. Okay. So this way, if you'll see, whatever will be the maximum height of a tree, that many maximum height of the stack is required. So that is going to be log n only. That is going to be log n. So let's assume that every cell is required k space, k space. Every cell is required k space, and that is going to be the height of the tree. That many stack cell you require, and every cell is taking k space. So k into log n is going to your log n only. See what I am saying here, whatever will be the height of the tree, that many stack cell you required in a recursion function. We have seen many questions. So height of the tree is log n, that many cell you require. Okay, that many cell you require. So space complexity is going to be k into log n, that is going to be your log n only. Okay, so let me write, since it is a recursive function, since now since it is a recursive function, 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 and for worst case, and for worst case log n recursive call can be made. Whatever will be the height of the function, that many recursive call can be made. And for worst case log n, recursive call can be made. Recursive call, recursive call can be made. Okay. So number of level, number of the number of level times the function can call, a number of height times the function can call, the function can call. So for every call, for every call let k space, k space let k space will be taken, let k space will be taken by stack. Let k space will be taken by stack. Therefore, let me write that. Okay. Therefore, for therefore for login call, login into k times will be the will be the will be the total will be the total space. So for worst case and even for average case, the time complexity, it will complete before your exam only. Since it is a 1 hour class now, so it will take time, but it will get completed in very good way. So it will take time. Means in it will go, but before your exam it will get finished. Okay. For worst case, either in November end or in December end, it will get finished. This year, I think it will get finished. For worst case, number of recursive call, number of recursive call is equal to number of level. So average case is also going to have the same. Average case and best case time complexity is going to say average average case. Sorry, average case and worst case space complexity is going to your big of log. Now, what is going to be the best case space complexity? What is going to be the best case space complexity? Please comment. In best case, what is going to be the answer? In best case, what is going to be the so for worst case, number of recursion call is going to be number of level. So average case and worst case space complexity is going to be of log n. So and best case space complexity is best case. See, whenever you are saying this best case space complexity, try to write in omega. Try to write in omega. Best case space complexity is going to be big O omega. Understood? So this we have seen Max-Heapify. This we have seen. If we have seen the space complexity is going to average case and worst case is going to your big O of n and best case is going to omega of n. Okay. Now tomorrow we will see building of max heap. We will construct a max heap. Okay, so in max heap what we are doing, if the left subtree and the right subtree is a max heap, then we are adding a element at the root, then we are finding a max heap. Now I will give you an array. Tomorrow we will see. Now I will give you any array. Now we like any randomly array, like 9 4 1, here 2, here 50. See, this is not a max. This is not a max. Okay, even left subtree and right subtree is not, left subtree is not a max. So here you can't call max everywhere. Now for this kind of tree, it is a complete tree only. It is a complete tree only, but it is not a max heap. So I will give you now in tomorrow class we will construct a max heap. I will give you a tree. I will give you a tree, complete binary tree, and you have to construct a max heap. That is build heap. Build heap is a function that we use to construct. See, these things are a part of a little bit of data structure. So from max heapify means it is going to do this. So should know that max-heapify is a function which is going to create a max heap if the left subtree and the right subtree is your, see, the left subtree and the right subtree is your max heap. Okay, if the it is applied only if left subtree and right subtree is max heap, then only. Okay, so hope it is clear to everyone. Now see, now we are going to see building. So now I will give you one array and you have to construct a building. Now the logic is that by using max heap I will construct. First I will explain with the example. Let me take one array, like first array I am having. So that tree I am taking here 1, then 14, then here I am having 10. So I am randomly taking one tree. Now that complete binary tree. Now see, I have told you that always the leaf is a heap. See, this is a heap, this is a heap, this is a heap. Why? Because left subtree and right subtree, it is not having any child, left child and right side. So it is the maximum only. So this is maximum, this is maximum, this is maximum, this is maximum, this is, so till this it is having the maximum element. Means it is a heap. These leaf roots are always going to satisfy the heap property. Always going to satisfy the heap property. Now from here I will call, now here I will call max-heapify. Here I will call the max-heapify. So if I call the max-heapify, then it will make this tree as max-heap. So 7, it is a max-heap only. Then I will go to here, it's a max-heap here. I am calling max-heapify here. It will be as it is because 8 is maximum from its child. Now I will go here. Now I will go here because you know the index will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I will go there on 3. So max heap I will call here. It is a max heap only. Now here I will go. It's a max heap only. Now here I will go. I will call. So now I am calling max heapify here. Then it will construct max heap here. Like here it will be 1. Then here it will be 8. Then 4. Then here 1. Okay. Now see, you are getting max heap. So what my logic is that we know that always the leaf is a max. So I will not call the max-heapify function in the leaf. What I will do, I will call the max-heapify function from, you know that number starting, you know that starting index of non-leaf. What is the starting index of non-leaf? From 1 to floor of n by 2, floor of n by 2, because starting index of leaf node is floor of n by 2 plus 1 to n. It was that. This was the starting index of leaf node. So this is the starting index of, this is the indexes of non-leaf. Please let me know whether it is clear or not. So 1 to n by 2 floor is the index of the non-leaf. Now what I am doing, I am calling the heap property from here, then here, then here, then here, then here. Then it is automatically making, from here it is making a, it's going and it's making a heap. It's going and making a heap. Let me take some other example. With some other example it will be more clear. Like take here 1, then 2, then 3, then 4, then 5, then 6. Now see, I am saying you that leaf is always going to, this is a heap max, this is a max, this because this is a leaf. Leaf is always going to be your heap. Now this 3, the 3 is not a max, so you are going to call. So here index 1, 2, 3, 4, 5, 6. So n is your 6. So now I'm going to call max-heapify from, for I equal to a dot length, a dot length by 2 by 2. Okay, and and I should be greater than equal to 1 and I minus minus, I minus minus. So now I will call max-heapify. I'm writing mh. Okay, max-heapify array. On this array, see, you know that we are storing the complete binary tree in array. Okay, so this is an array, and from index which I. So first I is going to your floor of this, a length is your 6, 6 by 2 is your 3. So max-heapify first is going to call on, max-heapify is going to call on a on 3. So max-heapify we are calling here. Why? Because left subtree is a tree. So left subtree हमारा क्या है? So left subtree is a max heap, and even the right child is not having anything. So this is a, this is left. So we can call max heap only when the left subtree is a max heap and the right subtree is a max heap. Yes, it is there. So here I am calling max heap. Now what max heap will do? It will make this tree as a max heap. So it will do this swapping here. 6 will come here because maximum should be at the top. At the maximum should be the root. So 6 is here, now 3. Now I am calling here. Now from here I am going to call. Now see, I will get reduced to, first I was here 3, then it will get reduced to 2, 2 greater than 1. Yes, now here I will call the max heap. Yes, it is. Now it is not a max heap, it's not a max heap. So now 5 will be here and 2 will be here. Okay, then I will get reduced to 1. Now I am going to call max heap here. Now I am going to call max heap here. So 6 will be here and 3 will be here and 1 will be here. After calling maxif, it will, now I will reduce to 0. 0 is greater than equal to 1. No, it will not. Now see, you got a maxif. You got to say here is 6. After like this, you are calling. So here you are not calling the maxif from the start node, because then again you have to do some things many number of times. You know that leaf is always going to be your heap. So that's why you are calling from non-leaf. That's why you are calling from a non-leaf. Am I clear to you? Please let me know how to build a heap. So by using max-heap property, I am building a max-heap. So now I will write the code. So I am writing a code, build max-heap. It's a max-heap and the array on array A. So a dot heap size, a dot heap size. So your heap size is going to be whatever will be the length of the array is going to the heap size, a dot length, a dot length. Now what I will do, I will create a for loop, and I will be, you assume int I. Okay, int I is equal to your a dot length. So array length by 2, array length by 2, array length floor, sorry, by 2. I will take the floor. So no need to even write floor. Array length by 2, it is going to your floor only. Okay, since it is a pseudo code, that's why I am writing floor and all. Okay, now I should be greater than equal to 1 and I should be I minus minus. I will call max-heapify on array A and I. Understood? See why I am calling from non-leaf? Because since all leaf nodes, since all leaf nodes are heap, all leaf nodes are heap first. Since all leaf node are heap, so we start so we start from non-leaf. So we start from non-leaf node from the last from the, since all leaf nodes are heap, so we start from non-leaf node, non-leaf node. So we start from non-leaf node till 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 node 1, till node 1. Okay, okay. Now we will see the time complexity and the space complexity of building. Okay, now we will try to find the space complexity and the time complexity. The, see, it is going to be, this is a function call. This is a function called Max-Heapify. Okay. So first try to find the time complexity. First try to find the time complexity. So you know that this loop is going to run from half times it is going to be run, half times, and every times when it is going to run Max-Heapify, you know that the time complexity and space complexity to Max-Heapify is big of log n, big of log n. So you might assume that n log n is going to be the time complexity. You may be thinking, because this loop is going to run till n by 2 times and the Max-Heapify time complexity is log n. So you might be thinking that n log n is going to be your time complexity. Okay, but it is incorrect. This is not going to be the correct answer time, because every time the height is going to be differ. So when, if you call Max-Heapify from the root, then only the time complexity is going to be log n, because height, it is always going to take whatever is the height of the tree, that is going to be the space complexity as well as the time complexity. Okay, so but here space and time is different, because always the height is going to differ. You are calling from n by 2, then like see here height is differ, here height is 1, then here height is 1, then here height is 2. So if you call Max-Heapify here, then here time complexity will be big of 1, big of 1, here big of 1, and here big of 2, whatever is the height. So we have to find here aggregate time complexity, not individually. So we have to add this big O of 1 plus big O of 1 plus big O of 2, like this aggregate. What is going to be that? Okay. So like this we can't say that. Am I clear to all of you? So it is not going to be n log n, because always the height of the tree is not going to be log n. So now we are going to find the aggregate time complexity, that we have to do this sum, because height is going to differ. Height is always going to be differ. Okay. So now time complexity, and you know that when height is h, how many nodes you are going to have at height h? At height h, how many nodes, maximum number of nodes you will have? I have taught you at height h. At height h, maximum number of nodes will be how much? Is going to your CIL of n by 2 to the power h plus 1. Is it clear? CIL of n by 2 to the power h plus 1, that we have seen in the previous lecture. So if the height is h, then at that height maximum number of nodes will be n by 2 to the power h plus 1. Now you have to call, you know that height is going to start from 0, height is going to be 0 till maximum height is going to be log n, maximum height. So you are going to do the sum of all, and you know that whatever, if it is having a in a height h, how many maximum number of nodes it can have? Floor of n by 2 to the power h plus 1, that many nodes you are having, that many nodes you are having, and every nodes is going to have how much time complexity? Whatever will be the height, so you are multiplying with that. See, it's like you, in this level, in this height 1, how many nodes you are having? 2. What is the time complexity of these two? 1, that you are doing into plus, then how many nodes you are having here? 1. What is the height here? 2, like this. And now you are doing the sum. See, that way I have written sum from height equal to 0 to log n. So how many nodes you are having at height h? This many nodes is going to have at height h, and the time complexity is going to be at height h is big O of h. Is it clear to all of you? Is it clear to all of you? Please let me know. Anyone having any doubt here? Anyone having any doubt here? Fine. No one is having doubt. See. Now see here. N is the number of nodes here. N is the number of nodes here, which is going to be constant, which is always going to be constant. And see, here it's big O. So when you want to remove big O sign from here, you just use one constant, that is ch. Okay. You can remove big O by using just constant ch. Now N is your number, and you can write it as 2 to the power h into 2. 2 to the power 2, if 2 to the power h plus 2, you can write as 2 to the power h into 2. Now you know that n is going to be constant, because n is number of nodes and 2 is going to be constant. So h is going to, here h, see, h is going to vary from 0 to log n. So the constant term I will take it out. So n by 2 I am taking out. C also I am taking out. Okay, c is a constant. Now it is going to be h equal to 0 to log n. H equal to 0 to log n. Here it will be h by 2h. Here it will be h by 2h. Now since here the sigma is going to do the sum from h equal to 0 to log n, if I can even write it as, I can write it as big O of 2. Now I will add the sigma. Big O, you know that it is going to be greater, h equal to 0 to infinity. I am now going to till infinity, because I am having a formula for h by 2h. If your if your sum is going to be h equal to 0 to infinity and h by 2h, then you are having a formula. That's why in place of log n, I am writing just infinity, so that I will get the value of that. And whenever writing, see, if it is number 2 equation, if it is number 1, since you are going the summation till infinity, so 2, since 2 is equation 2 is greater than equation 1, then equation 1. So we are writing, so we are placing big O. So we are placing big O. So that's why here I am placing big O. So we are placing big O. Is it clear to all of you? Now you know this value is equal to 2. This is equal to 2. So in place of, so big O Cn by 2 is going to 2. This is equal to 2. This is equal to 2. Okay. So since you can write, since sigma h to the power 0 infinity h by 2 to the power h is going to you 2. Okay, Madhuri. Madhura is saying to explain again from sigma. So this will get cancelled and you are going to get big of n. So time complexity is going to be big of n here. Okay, see here. You know that the at height h maximum number of nodes will be C log n by 2 to the power h plus 1. And here you are calling the max if you are calling the max if from n by 2, from n by 2 to 1. First n by 2, then n by 2 minus 1, then n by 2 minus 2. So that's why here always the height is going to be different. Always the height is going to be different. That's why I'm going to take the aggregate, that is the sum of all the heights. For different height, what is going to be the time at different height, the time complexity of max if is going to be different. At height 2 it is going to be height 2. At height 3, if we'll call the max pair, then its time complexity is going to be big of 3. So that's why we are changing according to the height. Okay, so I'm, and you know that height is going to start from 0 to log n, till log n it is going to be 2. Now you are going to do at height h, maximum number of nodes is going to be n by 2 to the power h plus 1. So if for this many nodes is at height h, so its max Heapify is going to take the time big O of h, is going to take big O of h. Okay, so when you are removing big O, you can remove the big O sign and you have to write a constant ch. Constant c is a, c is constant. Okay, so you can remove big O by using some constant ch you have written. Now, n is the number of nodes. N is number of nodes. So, number of nodes is always going to be constant. Since it is a constant, you have taken it out n, and 2 is a constant, you have taken it out. C is a constant, you have taken it out. Now, sigma is going to, summation is going to h equal to 0 to log n, h by 2h, h by 2h. Okay, h by 2h. Now here, since it was going to h equal to 0 to h equal to 0 to log n, so I can even do this sum h equal to 0 to infinity. If I'll do, see, it is asymptotic wise. So you can write in place of log n to infinity, then you have to place a big O. Previously it was having equal. Now since I am doing this sum more than log n, that is infinity, that's why equation 2 is greater than equation 1. So we are placing big O. So we are placing big O. Now this is a some function which is having the equal to 2, which is having, if you see the Michael's that your Corman, this means if you see that h equal to 0 to infinity, h by 2h is equal to 2. So in place of that I have placed 2, and now it is going to be n. Okay, so build heap time complexity is going to your n. Anyone having any doubt, please let me know. Madhura is saying yes. So this way we have find the time complexity. Now we are going to find the space complexity. Now we are going to find the space complexity. Now space complexity is also going to be the, so it's here, see, you see here space complexity. If you see here space complexity, it is going to run till n by 2 to this, and because of this is going to take constant time, this is the constant space. Only because of this max Heapify you are going to have the space complexity, only because of this max Heapify. Okay, only because of this max Heapify you are going to take some space. And when you are calling this max Heapify function, you are calling these from different height. So at max, when the max Heapify will take the maximum space complexity, when I will call from the root. When I will call, see, from here if I will call, it will take only one cell. If from here, then again one cell. If from here if I call, then it will going to take call from, it is going to take the maximum height is going to be at the root. Maximum height is going to be at the root. Okay, so maximum height is going to be this, because here you can't do aggregate. You are not going to do sum, because when you are calling from here, then you called maxify here. Okay, then it will return. Then when it will return, see, maxify you called at 3, it had done some work, it has taken space as big of 3, then it will release that, then it will release that memory, then again it will call here, then it will work, then again it will release that memory. So at max you require at the height. So at height, the maximum height of the complete binary tree is log n. Okay, so right, build max, build, is it clear to all of you? Build max heap space complexity, build max heap space complexity, space complexity. So build max heap space complexity will be same as, will be same as will be same as the space complexity, will be same as the space complexity. So build max heap space complexity will be same as the space complexity taken by max heap, by Max-Heapify a online, and it will take, and it will take maximum, and it will take maximum, it will take maximum when it is called, when it is called from the root, when it is called from the from, that's why, that's why. So when you are done with the writing, you can let me know. Okay, that's why space complexity is, that's why space complexity is big O of log n. So space complexity is going to be big O of log n, and time complexity is going to be your big O of n. Okay.